In lesson 6.4, we will be taking a look at something called Trig identities, trigonometric identities. These are equations that show us how one particular trig function can be equal to something else, or how different trig functions are related to each other in a way that might help us to solve equations, that might help us to simplify expressions. And so our online lesson tonight is just going to be going through what the 5 basic trig identities are that we'll be using, and then this will prepare us for what we'll do in class, which is to actually use these identities to simplify expressions. So our first identity is actually going to look pretty familiar to you. It's called the reciprocal identities. And if you think about what reciprocals are fractions, usually. If we start with something, a lot of times it's 1 over that something that is going to be our reciprocal. And so if you think about the trigonometry that we've done in the past lessons and in the previous chapter, we know that something like the cosecant of theta is equal to 1 over the sine of theta. Okay, so that is considered to be a reciprocal identity. We know that cosecant is the reciprocal of sine. Similarly, we know that the secant of theta is going to be equal to 1 over the cosine of theta. And we know that the cotangent of theta is the same as 1 over tangent theta, the reciprocal of tangent. But what we may not be as familiar with is the fact that these reciprocals are not just one-way reciprocals. So, the fact that the cosecant is equal to 1 over sine also leads us to the fact that sine could be thought of as 1 over the cosecant. Now that's not a particularly common way to write things, but if you end up with an expression where you do have 1 over cosecant, this equation, this identity, tells us we could replace that with just a sine. So we could also say that the cosine of theta is really just the reciprocal of secant, or 1 over secant, and we could say that the tangent of theta is really just the reciprocal of cotangent. So both of these forms are saying the same thing, but the different formats allow us to do different things and to simplify in different ways depending on what we get in our expression. Second type of identity is called the tangent and the cotangent identities. And again, we've already talked about one of these a little bit when we were talking about the unit circle where r equals 1. And so then sine is just our y, cosine is just our x. And that then leads us to the fact that tangent is the same as sine over cosine. Okay, now that also means that we can write an identity for cotangent. Going back to our previous slide, we just said that cotangent is the reciprocal of tangent. And so the reciprocal of sine over cosine is going to be cosine over sine. So again, a couple of identities that will allow us to rewrite things in different ways that might make it more, make things fit better so that we can actually simplify, cross things out, combine things easier, because maybe the fraction form works better than just saying tangent. Okay, here's another set of identities. This is one you will probably use a lot, because not only is the identity itself a very common one, there are also lots of variations of this identity that can be helpful. So let's start with the most common one. The Pythagorean identity is based on the Pythagorean theorem. Okay, and in the Pythagorean theorem, we know that a squared plus b squared is supposed to equal c squared. Now, if you think about what's happening in our unit circle, remember a unit circle is when we have a radius of 1. And so if I were to do a particular angle here, and we were to look at that triangle, the radius on this would be 1. So that means the c value here would be a 1. So we know that c squared would also give us 1. Okay? Now we know that a and b in a right triangle are supposed to be the legs. Well, in a unit circle with trigonometry, a and b are going to be the x and the y, which are also the cosine and the sine. So a squared plus b squared equals c squared becomes sine squared theta plus cosine squared theta, which will be equal to c squared, which will be 1. Okay, now the biggest thing to remember with this is that the sine and the cosine in these are squared. And we show squaring of trig functions by putting the exponent in the middle of the expression. If we write this, then it's not clear whether it's just theta that's supposed to be squared or if it's the whole sine that's supposed to be squared. So, in order to keep things clearer, we just put our exponent here in the middle, and then it's clear that it's the entire sine that is supposed to be squared. So this is the sine that's getting squared, this is the cosine that's getting squared, and sine squared plus cosine squared will be equal to 1. Now, the variations of that can also be very useful. For example, I could say that the sine squared of theta is also equal to 1 minus the cosine squared of theta. So that's just moving cosine over to the other side by subtracting it. That can also be very helpful sometimes. If we have sine squared in the expression, maybe it would actually work better if we were using cosine instead, so we could replace that with 1 minus cosine squared. Or, vice versa, we could say that the cosine squared is going to be equal to the 1 minus the sine squared. So this time it's the sine that's getting moved over by subtracting it. And again, sometimes having this version works better than having this version. So that's one way that we can modify this original Pythagorean identity to fit our needs. Another way that we can modify this is by dividing everything by a sine or a cosine. So let's change color here for this one. What happens if I take this sine squared plus cosine squared equal to 1, and let's say I divide everything by a sine squared. So all of these terms in my original equation, my original identity, are going to get divided by sine squared. Well, what that leaves me with then is sine squared over sine squared, well that's just 1, plus cosine squared over sine squared. Well, we know cosine over sine is cotangent, so cosine squared over sine squared is going to be cotangent squared. And then 1 over sine squared, again 1 over sine is cosecant, so 1 over sine squared will be cosecant squared. And so this is another Pythagorean identity that might be useful. And it just comes from this original identity, but having divided everything by a sine squared. We could also do a similar thing with cosine squared, excuse me. So if I have sine squared plus cosine squared equal to 1, so again my original Pythagorean, but this time I divide everything by cosine squared. Okay, so this time sine squared over cosine squared will leave me with tangent squared. The cosine squared over cosine squared will give me 1. And now the 1 over cosine squared will become secant squared. So this is another Pythagorean identity. So technically, we have 3 Pythagorean identities. Sine squared plus cosine squared equals 1. 1 plus cotangent squared plus 1 plus cotangent squared equals cosecant squared, and then tangent squared plus 1 equals secant squared. But all you really need to remember is just this one. Okay? Because if you can remember this one, then you can come up with these two when you need them. Okay, so really commit this one to memory, because this one's going to come up a lot, and you're really going to want to be able to pull that up just immediately whenever you see things that are being squared. All right, couple more identities here. The next type is called the cofunction identity, and this is based on the fact that sine and cosine are considered to be cofunctions because they're basically the same shape. When we look at the graph, they're just shifted. So if you think about what we've been graphing lately, we kind of know that with sine and cosine, there we go. With sine and cosine, well, darn it, sorry guys. We know that sine starts at our origin, goes max 0, min 0, and then we know that cosine starts at the max and goes max 0, min 0, max. Right? So when we put a bunch of these waves together, it becomes pretty obvious that they're really the same shape, but that they're just shifted over. This maximum here matches up with this maximum here, just shifted. And the shift is a pi over 2 shift. So what that means for us then in terms of the identities is that if I have, excuse me, if I have the sine of pi over 2 minus theta, that is the same thing as having the cosine of theta. And vice versa, if I have the cosine of pi over 2 minus theta, then that is really just the sine of theta. So again, this can be used in times where maybe simplifying sine into cosine would be much more helpful in the expression that we're dealing with. We also have one other cofunction, which is the fact that if I take the tangent of pi over 2 minus theta, that would give me the cotangent. So 3 more identities that we might find helpful when we are simplifying expressions. And finally, the negative angle identities. These are based on whether you rotate counterclockwise for a positive angle and how that compares to if you were to rotate clockwise for a negative angle. So let me show you what I mean. If we have our axes and I were to go up here for a positive theta, then a negative theta would move just as far but in the negative direction. Okay, so negative theta would be this way. Okay, so the question then is, if I take the sine of the negative theta, how does that compare to the sine of the positive theta? Well, if we were to make our triangles again, like we did before, and if we were to consider this to be a unit circle, where our radius was 1, then we know that the y is our sine. Okay, so this y value for the positive sine is a positive y. This y value, however, for the negative angle that we're taking sine of, that is actually going to end up being a negative sine because we're going down from our axes instead of up. So if I take the sine of a negative angle here, then that means it would be the same as the positive angle, but negative. And again, if you remember, all students take Chinese, this quadrant, this fourth quadrant, only has cosine positive. So we would expect that a first quadrant angle would be positive, but for sine, a fourth quadrant angle would be negative. Okay, so that's what happens with sine. Now, what's going to happen with cosine? So same idea, if I take the cosine of the negative angle, how does that compare to the cosine of the positive angle? Well, on the positive angle, the cosine now is our x. It's this distance right here. So on the positive angle, I get this distance for my cosine. When I take the negative angle, I still get the same x distance as my cosine. So for cosine, taking the cosine of a negative angle gives me the same answer as if I had taken the cosine of the positive angle. And then thirdly, if we take a look at what happens with, excuse me, with tangent, that we can refer back to our tangent and cotangent identity, where if tangent is supposed to be equal to the sine over the cosine, then we can set this up and say, okay, so what happens if I take the sine of the negative angle over the cosine of the negative angle? Well, we just set that up here. When I take the sine of the negative angle, we end up with the negative sine of whatever the positive angle would have been. And when I take the cosine of the negative angle, then we end up with just cosine of the angle. So I end up with a negative over a positive, which will give me a negative tangent of theta. So sine and tangents, if I have a negative theta, I would make a negative out in front with the positive theta. With cosine, however, if I take cosine of a negative theta, that's actually just the same as just taking cosine of theta. And again, that can be really handy when we're simplifying problems. So what you need for tonight is simply to have these identities written down. Maybe you write some of the examples or some of the reason behind it, but all you need is just to have these examples written down so that in class tomorrow, as we start going through simplifying some different expressions, you can refer to these identities and start using them. And with that, we will see you next class.